Alright, so in the previous video we got a good idea about the complex plane, or we got an introduction to the complex plane. So in this video we will look at how we actually use that knowledge about the modulus and the argument to write our complex numbers in a new way. And the new way will be on polar form. So let's just start by looking at the complex plane one more time. So if we have the complex plane here, we have the real axis here. And then, of course, we have the imaginary axis here. So let's just start by looking at a complex number c that is equal to a plus ib, just as we always look at a complex number. Okay, so everything we really need to describe this complex number c is just the real part and the imaginary part. So it's just a and b. Given a and b, then we can just go into the complex plane and we can say, okay, a is here, b is here. Okay, so our complex number must be here. So just by having these two numbers, a and b, then we can describe every complex number in the complex field. But we would like to do something similar, because if we look at the modulus and the argument, then we can actually do the exact same thing, because we can get to any point in the complex plane just by knowing these two numbers about a complex number. Because if we know the argument, then we know how much should we go around. So for example, if our complex number was here, we would know we have to go this much around, and then we have the modulus that says, okay, we have to go all the way out here. So in that way we can reach every single number in the complex plane just by these two numbers, the modulus and the argument. All right, and in the previous video, I of course recommend you watch that if you haven't seen it already. We saw that the modulus r, we could find that, and we also called it the length of the complex number, and we could find it as either the square root of the complex number c multiplied with the complex conjugate, or we could just say it's the square root of a squared plus b squared. All right, and we also saw that the argument, we could find that by taking arctan. Here we go, arctan to b over a, so the imaginary part over the real part. So if we just take arctangent to b over a, then we find the argument. All right, so let's just imagine we have our complex number here, c, and we know from the previous video that this would be r, the modulus, and this is the argument. And if so, just like I said, these two numbers, they can describe our complex number, but we might as well use a and b. But we know that our normal form of a complex number is c equal a plus ib. So now we're interested in expressing a and b in terms of r and theta. But how do we do that? Okay, let's look at the complex plane here and the drawing I have just made. So from SOHCAHTOA, like we used in the previous video, we know that cosine of theta is equal to the adjacent. So that's the adjacent over the hypotenuse, just as we did in the previous video. And okay, the adjacent, that is just this line, and the length of this line is just a, and the hypotenuse is r. So it's just gonna be a over r. All right, but what we are interested in is actually r. So let's isolate r by multiplying with r on both sides. So we get a equals r times cosine of theta, the argument. All right, we can do the exact same thing for sine. So if we take sine of the argument, then it's equal to the opposite angle, the opposite side over the hypotenuse. And that is just equal to, well, the opposite was just this line, and that is just the same as b, our imaginary part of the complex number c, so it's b over r. And once again, what we are really interested in is b, so let's isolate b by multiplying with r. So we get b equals r times sine of the argument. Perfect. Now, these two results are what we're gonna use now, because we already have c expressed over here. So let's just plug in our expressions for a and b. So for a, we have, it's the same as r times cosine of theta. That's exactly what we just found here. And then we add plus I is still there, the imaginary number, but instead of b, we're gonna write r times sine to the argument. So it's r times sine theta. There we go. All right, but we can see that if we look at this, we multiply with r on both sides, or not on both sides, but on both terms. So let's put that outside. So what we get is r times, and then we have cosine of the argument plus I times sine theta. There we go. So this is our new way of expressing a complex number on polar form. And this will be the main reason we're gonna express our complex numbers in the future. So this is very useful to know. And since it's so useful, let me just add what the real part and the imaginary part is. So the real part, let's do it in this color. The real part of C, when we have it in polar form, that is just r times cosine of theta. And the imaginary part, that will just be the imaginary part of our complex number on polar form, that would be r times sine to the argument. There we go. So there you have it. That's how we write complex numbers on polar form, and the motivation for why we write it this way is what you just saw here. And as I said, this will be the new way that we're going to look at complex numbers almost every time. So it's a very good thing to remember this, and especially this form of a complex number. In the next video, I think we are gonna go to a new topic. Or not a new topic, but we will look at multiplication and division in polar form. And this is a brand new way to look at it. It's gonna give you a geometrical interpretation of multiplication and division. Before, in the video, I think it was the 5th video, it was a little hard to comprehend what happened. It was just a lot of not numbers, but a lot of letters. But in the next video, we will get a geometric interpretation of multiplication and division.